before that, I want to address a general problem of relating two sets of fluxes and the various driving forces. So, some of the common, firstly, definition of the so-called convective flux that I haven't defined explicitly can be defined for any species. And we have seen 4 types of diffusive fluxes. Of course, there's also the N alpha. And then we have these 4 types of diffusive fluxes: A alpha star, A alpha star lowercase, and then these are some of the diffusive fluxes defined for each component. Right? Convective as opposed to the diffusive fluxes. And then we also have the various driving forces. The driving forces can be either density gradients or concentration gradients. So we can have or we can have the most common one on the here again I would say this is alpha equal to 1 to C, whereas this is alpha equal to 1 to C minus 1. If the diffusive flux can be defined for all the C components, only C minus 1 of them will be independent. So it's important to keep that in mind. In the same way, whereas the density gradient for the C of them independent, the mole fraction, the mass fraction gradient, there are only C minus 1 which are independent, because the C mole fraction is simply given by the other C minus 1 mole fraction. If I know the gradient of C minus 1 of the mole fraction, I know the gradient of the C mole fraction also. So, for instance, if you look at, for instance, the table 17.82 of first thing, it gives a fixed first law in various forms. I will leave it as an exercise for you to show the equivalence between the various forms he has given. But as an illustration, I will take 2 of them. So the most common form of the fixed law is for this is supposed to be for a binary. It is defined like this. I mean, this is a definition, but what the fixed first law says relates the mass diffusive flux with respect to the mass average velocity to the mass fraction gradient to this form. Right? And also you will see that the molar diffusive flux with respect to the molar average velocity is also expressed in terms of the mole fraction gradient, and it so happens you have to prove this actually, the 2 are actually equivalent. Right? So clearly what we need is a relationship between the mass diffusive flux on the one hand, the molar diffusive flux, and the mole fraction gradient and the mass fraction gradient. So this is a general problem in which the problem of relating these fluxes and gradients is extends to multi-component mixtures as well. Right? So we don't want to be restricted to the binary mixture. So what is really needed here is a general relationship between A alpha is 1 to C minus 1. How are they related to the C minus 1 molar diffusive fluxes? And then how those are related. So if I know the expression for the arbitrary C component mixture, certainly I can binary. Although it might be easier if you're just interested in expressions for the binary, you should just directly look at the binary. But I want to develop a general method of relating these fluxes and mass fraction of the driving force, flux and the driving force. How can they be related? So we'll take up first the relationship between let's say I have A alpha. We first look at the definition. Right? And then on the other hand I have A alpha star, which is C alpha. So I can start with any one of them, but I'm going to outline a systematic procedure so that you don't get mixed up in the indices and try to eliminate and so on. Right? So I take this up, I can either start from this or from this. I can start from one of this. Right? And then I see here the B alpha can also be expressed, that's a key point, B alpha, where it appears in both. So if we want to express A alpha in terms of the you find that you will get all the C minus 1 mole fractions the molar fluxes in general, right? So I need to, so one way is to simply write this as rho alpha times B alpha can be written as J alpha star by C alpha, right? Plus B star, talking with the B star, we see will cancel out. That is also expressed in terms of velocity, but it is appearing here as an isolated, as a separate term. And then, but I still have this. Now B is this we know. So again, I write this as Wj times Bj again I will substitute. This is in terms of alpha, but anyway it doesn't matter. Maybe I can just make this Ji. That might be easier. We used to using i's and j's. I just stick to that. And a equal to 1 to c j times Vj. Again, I will substitute. Right? The expression for Vj from this, and that would be J star by Cj plus V star. And this whole thing is written the bracket. Now if you look at this, there is a V star here minus sum over j equal to 1 to c wj times V star. We look at that term. V star is not part of the sum, so it can be taken out. Right? So I can write this as sum over j equal to 1 to c wj times V star. So V star is a term with factor in each one of the terms. It can be taken out. Right? So this is equal to 1. And so it conveniently cancels because there's a minus sign here with this term. Right? That term will fall out, and the net result is that I have rho I times Ji star by Ci minus sum over j equal to 1 to c wj by Cj and Jj star. This is what I have. Now clearly, what I have here are C of the molar diffusive fluxes, but I know that only C minus 1 are independent. So what I really want is to write J1 in terms of AC minus 1 of the Jj star. Right? But I have all C. I know that not all of them are independent. So C minus 1 only are independent. So I can choose a set of independent molar diffusive fluxes of J1 star, J2 star all the way up to Jc minus 1 star. So I have to basically eliminate Jc star from the equation. So I know that sum over J equal to 1 to C J star equal to 0. So I can easily write this as from this Jc star and written as minus sum over J equal to 1 to C minus 1 J star. I can write it like that. So what I'm going to now do is rho I times Ji star by Ci minus, I have sum over J equal to 1 to C minus 1. Only I will write first. Minus Wc by Cc. The substance C refers to the C component. Jc star. Okay, I'm just writing the C term alone separately. Jc star is given by this, and so that with a negative sign would become plus times sum over J equal to 1 to C minus 1 J star. So which can now be written as rho I times Ji star by Ci minus sum over J equal to 1 to C minus 1, right? So Wj by Cj minus Wc by Cc J star. So I have now achieved what I wanted. I have expressed a particular mass space, mass diffusive flux with respect to the mass average velocity in terms of the C minus 1 molar diffusive flux with respect to the molar diffusive velocity. Now, in principle, I can do it for relation for any set of terms. I mean, a good exercise would be start from this and try to express it in terms of Ji, smaller, lowercase j. If you look at the crucial steps here, the crucial steps are simply I notice that there is a velocity here. And I notice that all the species velocities come into the picture as equivalent. It could be any as it could be starting from here and start with P star. Right? So all that you have to do is my objective is to express this in terms of these. So express each velocity, each species velocity in terms of the diffusive flux which I want. What I am saying is this procedure will apply in general. Right? Then the next step is to eliminate the flux which is not independent. Right? So there is one of them which is not independent. So that is the next step. So I need relations like these to eliminate and get only the set of independent fluxes. In this case, there is only C minus 1. You look at the convective flux, which are not usually used directly because the Fick's law or the generalized Fick's law for multi-component mixtures will relate to the diffusive fluxes. Right? So we are focusing on that. So there will always be the diffusive fluxes. Whatever type of diffusive fluxes you take, you will see that only C minus of one of them would be independent. So I've got this. There is still one final step. If you want to express, for instance, if I want to express this in terms of a matrix form, so I want J, C minus, each one is a vector, but then I have a vector of fluxes, and you can clearly see that this is of the form of some coefficients multiplying J1 star. I can clearly express this. To do that, I need to recognize that there is an I here. You will see that if you are relating Ji, the ith mass space diffusive flux, the coefficients are the same, right? They are related to the J component, but then for the Ji related to Ji star, alone, there is an extra term coming here. Right? So I can write this slightly differently or equivalently as rho I times, then I have Ji star, right, which will be multiplied by 1 over Ci. Right? So what I am going to do is I take the ith term from here and put it there. So you can clearly see how the coefficient of the matrix can be written. Right? So the coefficient of the matrix will do like that. So I take the ith term along, so that would be 1 over Ci minus, right? So minus Wi by Ci plus, there is a minus here, plus Wc by Cc. That is all there is for the ith coefficient of the ith molar diffusive flux. And then I have minus sum over J equal to 1. Now the ith term is no longer there, it has been taken out. So it is usually conventional to represent this by J equal to 1 comma I, which means the ith term is not to be included. C minus 1 times Wj by Cj minus Wc by Cc. So I can easily write, for instance, if I were to write this as a matrix A, you can clearly infer by inspection coefficient Aij of the matrix. Because if you have C minus 1 rows and C minus 1 columns, so what is the coefficient? So you can clearly see that I would have to include this separately. Right? So the diagonal elements of the matrix will have these coefficients. So this relates Ai star to Ai capital star. Right? So I can write this then as delta Ij times 1 over Ci minus of Wi by Ci minus Wc by Cc minus Wj by Cj minus Wc by Cc. So that for the diagonal, for all the off diagonal terms, this will not be there. Right? So all the diagonal terms will have diagonal elements of the matrix will have the additional terms. So I am indicating it with the delta I. Otherwise, the coefficients are the off diagonal terms are looking very similar, can be written in a certain pattern. Right? So what I want to do, this is very general. It's not really that much relevant to the particular problem I have. So I can now apply this for the binary mixture and verify whether I am getting the same result as what words to Lightfoot have got, right, in that table. Right? So for binary mixture, the notation is slightly different. So C is equal to 2. That is the total number of components is 2. And I am going to label them as A and B. That's the standard notation. Rather than calling them 1 and 2, we call them as A and B. To be consistent with the notation. So there will be one diffusive flux, independent diffusive flux for the J, and then there is one for capital J. So I can choose A as that component, right? JA. I'm going to rightly write this formula. There is no question of matrix here. There is only one element, right, in that matrix. So rho A times JA star times 1 minus Wi is equal to A here, right? So that's what I am using. 1 minus Wa by Ca. So what is the C component here? B is B. So C is one that is not included in the set of independent fluxes. So there is only one independent diffusive flux. I am choosing it to be that referring to component A. I can also choose it to refer to component B. Right? So I am now making I equal to A. There is only one component that is one independent diffusive flux. So the one that is left out is obviously the component B. So B, right? And now what about this term? Will I get anything out of this term? I'm sorry, there's some problem here. A star be there. So j equal to 1 comma I is c minus 1. C minus 1 is 1 here. So j equal to 1 comma I means 1 cannot be there. Right? So there's nothing that is going to come out. This is the problem with interpreting this for a binary mixture. So you have to understand that this term will simply not appear for the, because this has all, this is the I, so this is the first. If for instance it were part of a ternary mixture and I'm writing J1 star, right? So J1, this would mean that in this sum, 1 should not be there. And here, all I have is the sum corresponding to j equal to 1 comma 1. So that means 1 cannot be there. Going to 1, right? So this term will simply not appear, and all I have is this. That's the only term that will count, right? Because I have already removed the. Otherwise, if you are confused by this, you can simply go and apply it here. Here, j equal to 1 is even, there is another term that will come. If you are confused by the comma I, right? You can simply apply it to this. This is as much a valid formula as this. Only that to write it in a matrix form, I need to rewrite it slightly differently. Right? This is a complication that comes in multi-component mixture. But for binary, it's very straightforward. In fact, you don't even have to do all of this. If you are just focusing on binary, you can actually start with JA and JA star and try to relate the two. That would be the simplest. But I'm pointing out a more general procedure. You can do that. I leave that as an exercise for you. Just focus on JA and capital JA star and work out the procedure. Right? So that is what we have. So let us now work on this. So clearly we have all of these conventionally expressed in terms of the molecular rates. Right? So we have all those relations. We have what do you have? So I can write this as rho times WA times 1 minus WA by C times XA plus WB. It is also 1 minus WA. I'm sorry, 1 minus. Yeah, I can write this as WB actually. Make it simpler. This will be XB. Right? So I can take the C out. So rho over C, WA, WB times 1 over XA plus 1 over XB, which is equal to rho over C is the average molecular weight. We have seen that. So that will be M average, and this will be XB plus XA, which is 1 divided by XA XB. And I know that WA by XA is simply, what is WA by XA? Right? WA is rho A by rho, and XA is CA by C. Right? So WA by XA is rho A by rho times C by CA. Right? Rho A by CA is MA, and rho by C is M average. So I get MA by M average. This will be MA by M average. That will be WA by XA. And then I have WB by XB. That will be MB by M average. And then you get MA, MB by M average. So we have the J star. And related the mass-based diffusive flux to the molar-based diffusive flux. Now, all that is required. If I want to further relate this, I want to relate the mole fraction gradient, the weight fraction gradient, right? So again, I can start from either one of them. So what I will do is simply look at what is the formula for. Again, I will move to the C component. Right? Once you know how to do it for C component, you can do it for two components here, right? So I can write the general Wi. So I want to write this obviously in terms of the mole fraction. So I want to express the gradient of the weight fraction in terms of the gradient of the mole fraction. So I take a particular weight fraction of a component I, right? Again, go by definition, go y by rho, right? So then I want to move to mole fraction. So I will move to concentration, right? So I will rho I is simply Ci Mi, right? And rho is simply C times M average. Wi is given by Mi Xi by M average. A crucial point to know is that M average is obviously right, there is a J equal to 1 to C Xj Mj, and so if I leave it as it is, because now I want to take the gradient of this. When I take the gradient, I will get the gradient of all the C mole fractions, but I know only C minus 1 of them are independent, right? So again, I have to write this, for instance, the sum of J equal to 1 to C minus 1 Xj Mj plus Xc Mc. The same thing I did with the diffusive fluxes. So we have to eliminate. If we leave it like that, fine. There's nothing wrong with it. But it's typically not done because we know that only C, when we have to teach only C minus 1 quantity, why do you need to have an additional term, right? So Xc is nothing but 1 minus sum over J equal to 1 to C minus 1 Xj, right? So that could be then sum over J equal to 1 to C minus 1 Xj Mj plus Xc is 1 minus sum over J equal to 1 to C minus 1 Xj times Mc, which means that M average is given by Mc plus sum over J equal to 1 to C minus 1 Xj times Mj minus Mc. Now I have written the M average in terms of only the C minus 1, which I can choose. I can choose any C minus 1 of them, right? So now I can easily take the gradient. It's just like differentiation. You are going to apply directly the vector operator. If you are confused, you will differentiate with respect to x, and then with respect to y, and with respect to z. We can directly do the gradient operator. So let's see how the gradient operator will work. Right? So Mi is a constant. You have to remember M average is not. It's composition dependent. That's often you might miss out. Right? It will obviously be tempting. Simply write this as Mi by M average times the gradient. Let's say relatively one term. We have to handle the dependence of M average on X, and that's why we have to go through all of this. Right? So Mi, so I have to apply the quotient rule. M average squared, and then this will be M average times the gradient of Xi minus Xi times the gradient of M average. The gradient of M average will have nothing, right? The gradient of M average would be sum over J equal to 1 to C minus 1 Mj minus Mc times gradient of Xj. So then again we can do the same thing right in terms of a matrix. There's a matrix that relates the set of C C minus 1 mass fraction gradients, each one of which is a vector, right? And so I can write this as mi times, this would be 1 over m average times, and in fact I get another term from here, right? So this would be xi times 1 over m average, and I'm going to get another term from here. I'm going to pick the ith term from here. That would have minus xi times mi minus mc, right? And then minus xi sum over j to the 1 comma I, c minus 1 mj minus mc, and of course I will have also this an m average square here, and that will also be so I have this. So you can again write, I infer what the matrix coefficients are, but now what I want to do is to apply this from the binary mixture and see what I get. So for the binary mixture, since I have chosen the component A, the gradient of the weight factor, that's what I will choose. So that would be is equal to, it would be MA, and again this term is not going to appear because it doesn't have the ith contribution. That's all I will have. There will be one independent mole fraction here, so I can very easily write this as MA times 1 over m average minus XA times MA minus MB clearly by m average square. So I can take an m average out and I will simply get m average, right? Gradient of XA. This is what I have. So now this can be written as MA by m average, and m average is I know XA MA plus XB MB minus XA MA plus XA MB XA, and so this will cancel. So this is XA plus XB times MB, that is 1 times MB. This would be MA MB by m average times this. So that's also I have got. So if you're confused about having to, you don't have to go, if you're interested only in the binary, so you don't have to go through all these somewhat complicated questions. As an exercise, I will say directly take A and B and try to do it and verify whether you're getting this, right? So now it's very simple. So I have got this A I have expressed in terms of A star, that would be MA MB by m average times A star minus rho, since I want C, right? So rho is simply C times m average. We've already seen that, how that would work, right? Times DAB, and then I will substitute for this, that would be MA MB by m average times the gradient of XC. So I can obviously cancel a whole lot of terms. This is an MAB square, right? Here. This is an MAB already. So this is going to come again in the denominator, right? So this is MAB minus, that's what I written, divided by MA. So there will be an MAB square. So that unit is going to get cancelled. I need an MAB square. And then this will get cancelled with this. So from this I get A star equal to minus CB AB. So we have assume that the two sets of equations are equivalent. And you can see that that is the one that relates. That's why these are most popular, because if you go and see that table that I referred to in verse like using the other fluxes, he has written in terms of various other concentration gradients and other types of gradients and other types of fluxes. You see the formula are not so simple and straightforward. So that is why these two fluxes are commonly used probably. This is the mass average diffusive flux with respect to the mass average, mass diffusive flux with respect to the mass average velocity that is related to the mass fraction gradient has very similar form to the molar diffusive flux with respect to the molar average velocity that is related to the mole fraction gradient. The only difference here is that here you have the loading density, here you have the loading concentration. Right? So this will summarize what I have to say. First exercise would be to go to table 78, whatever, and you will derive the other relations using the same procedure. Right? So you have to first know the definition of the various fluxes and then what you want to relate it to. Right? And then you have the driving forces, what they are and how they are related. All the sections we have already put given all the possible relations between the various densities and weight fractions and mole fractions and so on. So with all of that, all it requires is you take into account the fact that there are likely only some of them might be independent, and so you have to eliminate the ones that are not independent. Either it be in terms of the diffusive fluxes or it be in terms of the driving force. So let me now take up a simple, a very famous and standard problem called the Stefan cube. It is used to measure diffusivities of the gases. Right? So what you have here is that you basically have a liquid. Let's say I call this liquid B. Actually called A, and then you have a gas on top of it, and so this is sort of evaporating from here and diffusing into a B. Usually a pure B is flowed past the top of the tube. So you have liquid here, and then you have gas flowing. So it's a question of A evaporating from here, and what you have in the gas is actually, you're not considering the diffusion in the liquid. The liquid is effectively A, which evaporating, the vapor of A is mixing with the B gas and diffusing, right? And by analyzing the composition profile and the fluxes, right, you can calculate the diffusion coefficient DAB. We'll see how that is done. So there are several approximations that are employed. We'll see how these equations lead to an approximate solution. So, approximations are assumptions are liquid level is maintained constant. So, actually it's a moving boundary problem. If you want to look at the transient problem of the liquid level, obviously if you're going to evaporate, liquid level is going to come down. But for the purpose of this problem, we assume that the liquid level is somehow maintained constant, or is not changing drastically. Right? And you call this the z-axis. Z. So this is called z equal to z1, which is z equal to z2 as per the notation. Then we assume that B is insoluble in A. B really doesn't dissolve in A. So I can look at this as a liquid in equilibrium with A and B at the surface. So that will give you what the approximate composition of A would be here, right? And then we assume B is stagnant. That is, there is no significant velocity for B. So it's basically not a convective problem, but effectively a diffusive problem. There is nothing that is forcing the flow. It is evaporating, and there is a gas flowing past, but in the tube we assume that B can be considered as stagnant. It's not significant. This is an approximation. There have been many more improvements of this solution, but we'll see how the simple approximation of obviously one-dimensional diffusion from the z direction alone. It's a very straightforward problem, provided you understand and implement these assumptions, right? Huh? Yeah, temperature, pressure, everything is fixed. So these are all the approximations. This is a very zeroth order solution, you can say. Right? So now, how do these equations, what do they give? They are obviously assuming the Fick's law. Here it is conventionally writing as the molar diffusive flux. So what is, for instance, the continuity equation? So you have, that's all we have actually. We have the two continuity equations. And the one dimension means all I have to consider is the z direction. All velocities, everything would be in one dimension. So the continuity equation, which is applied for the component A, is this. Right? For this problem, we are assuming the system has reached a steady state and no reactions, the system has reached a steady state. So rho Ca by dt plus this is the continuity equation, no reaction. So this is steady state. At steady state, this is what we have. So the one dimension is d by dz of Ca Vaz is equal to 0, which means Ca Vaz is a constant. Right? And you call it now we are going in the Fick's law, right? Fick's first law. So this basically NAZ is a constant. I mean, as you like to say NA, because there's only one dimension, right? We've understood that it is along the z direction. Now, what the equation that is standard in this is that NA is equal to XA. Fick's first law, I have to write this as Ca times Va minus V star plus Ca V star. So this is the Ja star wave. So I am assuming that this is given by the Fick's law. So this would be dXA by dZ. What about this? Right? So Ca V star. The V star is right? V star is Ca Va plus Cv Vb by Ca plus Cv. So I can write this as Xa Va plus Xb Vb. Now we are looking only at the z direction, so the z star would be Xa Vaz plus Xb Dvz because of the stagnant B assumption, right? So effectively that would mean that we are not looking at the velocity of B is taken to be 0. In that approximation, we get dz star is Xa Vaz. So this would be Ca times Xa Vaz. This also is Ca Vaz. All one dimension. So I can easily now bring in. So this interestingly gives a solution. Sort of the first step to the solution. Vz times 1 minus Xa is minus C dxa by dz. So CA is a constant, right? So I can write this as C times XA right? And so C and C would cancel. Now if CA is a constant, right? Then C times XA is a constant. Now because the temperature and pressure are fixed, if I assume an ideal gas mixture for which C is actually P by RT for an ideal gas mixture, volume number moves by volume, that is C by RT, local statement of the ideal gas mixture. If we keep P and P fixed, then C is automatically fixed, so which means XA is some constant, some other constant, and I will call this as some C1. So what I get here is that C1 times 1 minus XA is minus dAV dXA by dZ. So we have a first order equation in XA, right? So this is somewhat a simplified and a direct solution which you will not get if, for instance, you can directly write the Fick's second law. That will lead to a second order equation in XA. If you try to solve it, you will find that one of the integration steps is already done. If I directly use this equation, this is kind of a thing that works in the special case, right? So C1 times 1 minus XA. So C1 is yet not known. I have a first order equation in XA. So there is one constant that will come by integrating this, and then on top of it there is C1, right? So there will be two conditions I have to provide to determine C1 as well as the ones that I would get out of the integration constant. This is done by simply specifying XA1 and XA2. Typically XA2 will be seen because you have pure P flowing past the top of the cylinder with a tube, right? So then we can solve it and get the solution. We can use it to get the diffusion coefficient. You see how it works out in Monday's class. So that would be the last class. So we have a class on Monday at 8 o'clock and wrap up the course. You consider a couple